Okay, we're going to combine these two together. The work is so similar. As soon as you pass up the equivalence point, you have consumed all of the weak acid, and you've converted it all to its conjugate base, and you are continuing to add more sodium hydroxide. So what you have is a mixture of a strong base and a weak base in that solution. And anytime you have a mixture of a strong and a weak, you can base the problem entirely upon how much strong is left over. So in this problem, we have passed up the equivalence point. For the first one, we have barely passed it up, so maybe at G, and then we've gone a little bit further at H, and we're going to be able to calculate the pH of those two. The beginning work, you don't need to know you're at beyond the equivalence point when you start this problem, because it will become evident as you work the problem. We'll start with the same generic reaction, HA, that's the weak acid, reacting with the OH minus to produce A minus and H2O. We know this is a one-way reaction, so we will do an ICF table. All along the way, the amount of the acid has not changed, 4.98 times 10 to the minus 3. But now we've passed up the equivalence point, and let's figure out the moles of OH minus. Now we know it's the same as the moles of sodium hydroxide, so we'll take the molarity of sodium hydroxide times the volume in liters, 0.02005. So I've just barely gone past the equivalence point, but that's going to be, the value ends up being 5.1, and I'm going to go ahead and carry an extra sig fig here at the 5 times 10 to the minus 3 moles. So that is, don't see my O there, that's the OH concentration. So it's 5.105 times 10 to the minus 3. For the reaction, there's none of this, and we don't care about the water. Now, between these two, the acid is the smallest value. So we're going to subtract it from both reactants and produce 4.98 times 10 to the minus 3 here. We subtract these two numbers under HA and we're left with 0. We subtract these two numbers under OH minus and we're left with 1.25 times 10 to the minus 4. And we have 4.98 times 10 to the minus 3. By the way, this 5 is not significant. I'm just carrying it extra for now. Okay, so what do we have left? We have a strong base and we have a weak base. And when you have a strong base and a weak base, the strong base will dominate the solution. So what we will need to do is we will take this value and be able to calculate the pOH from it almost. Keep in mind that this table is values of moles. If we're going to calculate a pOH, we're going to need the negative log of the OH concentration. So to get the OH concentration, we'll need the moles over the liters, and at this point we have 20 milliliters of the acid, we have 20.05 milliliters of the base, that's 40.05 milliliters, or 0.04005 liters of solution. When I divide those out, this portion right here, it is 0.00312. That is the concentration of hydroxide. And when I take the negative log of that value, I end up with 2.506, which actually we only know it to two significant figures, so that would be 2.51. We will then, to get the pH, we will take 14 minus 2.51, and we will obtain a value for the pH of 11.94. Sorry, that's not correct. 11.49. I said it with dyslexia. Okay, so there's your value of the pH. We stop and think, should it be above 7? Certainly. We have a base left over, so it should be above 7. Now, we'll just talk through the difference for that problem and if we were doing letter H. For letter H, we have a higher volume, so this number would be different. We would end up with more base left over, and you will be able to go through all the same procedure that you followed here. I would like for you to give it a shot, and when you do, see if you don't get H's value to be 12.44. So it goes up a little bit more as you add more base, and it will continue to rise as you put more and more base going past the equivalence point.